And welcome students to another lesson for binary and hexadecimal. Today we're going to talk about converting to and from decimal. So if you recall, binary we've said is represented using either a 0 or 1. Binary is of base 2, hence we have 2 digits that we can represent here. Decimal is represented using 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. All right, decimal is of base 10, hence we have 10 digits. Now today we're going to look at doing some conversion between the bases to better help us understand how the computer converts our decimals into usable code, because remember, computers are only using binary. So let's start simple. Let's start with one place value. In binary, if you recall, this is only 0, 1. Conveniently, in decimal, this is also only a 0 or 1. However, if we want to work backwards and go from decimal to binary, we would run into a problem. Since the ones place in decimal goes from 0 to 9, there's no way that we can fit all 9 digits into the first digit of binary. It doesn't work. You try shoving 10 things into the slot of 1 or 2, it doesn't happen. Now, why is this? Well, this is why this is. Binary, like I said, uses powers of 2, while decimal uses powers of 10. Therefore, when we are looking at place values, regardless of the base power, whether it's 2, 10, 16, 8, it doesn't matter, the place value is determined by whatever the power is at that point. So the number of place values is going to be the same thing as the power. So with decimal, we're using powers of 10. With binary, we'll be using powers of 2. And I'll explain this a little bit more in the next few slides. So let's start first with the power of 2 place value. Let's re-examine an 8-digit binary bit. Here I have 0000000, all right, which is equivalent to 0. Now, what we need to take away from this, though, is that there are 8 place values. And we can say that this goes all the way up to 2 to the power of n minus 1, or the number of digits minus 1. So there are 8 digits in this binary bit. So that means that it's 2 to the power of 8 minus 1, or 2 to the power of 7. Now, why n minus 1? Why do we have to take 1 back? Well, the reason for this is because that first place value is always regardless of base power. So whether it's 2, 10, 16, anything like that, that first power is to the power of 0. So it would be 2 to the power of 0, 10 to the power of 0, 16 to the power of 0, whatever that place value is, that first digit that's right here in that string there is to the power of 0. So let's look real quick at some binary place values. In this chart here, you can see I've labeled out, you got 2 to the 7, 2 to the 6, 2 to the 5, 2 to the 4, 2 to 3, 2 to 2, 2 to 0, 2 to 1. And if you look, you can see our 8-digit binary bit. So 0, 0, 0, 0, 0, 0, 0. Okay, there's all zeros are just plugged right in there. Now, a similar thing occurs in decimal as well. I just filled the next chart in with some values, kind of represent the same thing. All right, obviously it's not equivalent to this, but it's something that's a little more familiar to us when we look at with the binary place values here for the tens power. So here's 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, and 10 to the 4. So you can see here 10 to the 0 is just 0, which is the ones place. 10 to the power of 1 is 10, it's 10's place. 10 to the second, 100 is the hundreds place. 10 to the third, 1000, 1000's place. This is something we're very familiar with. This, not so much. But don't worry about this chart because we're actually going to do something that's going to help us with this. This is something that we're very familiar with. We work in the decimal system all the time. Right? Each place value here is representative of a power of 10. It's very familiar to us. Now, how do we do this conversion? While there are tools that exist for us to convert between binary and decimal, like you can just go right to Google and do binary to decimal calculator. In fact, I had you do one earlier where you just plug the number in, it did the conversion for you. You didn't have to do any math. Well, we're going to need to know how to do so for the converter. In some of our quizzes and stuff, you're going to have to do that without the converter. So you need to know how to do that. So let's start here with a simple binary bit. Here I have 0, 1, 0, 0, 1, 0, 1, 0. Now, if you don't know what that is in decimal, do not worry. You will be taught how to convert. Right? Some of you might say, well, I know what that is. That's this number right here. Don't worry about it. We're going to get everybody on the same page. Now, I'm going to provide you a copy of the flip chart that's going to help you aid in your conversion between the two systems. Now, an example of how to do the binary bit above is starting to be shown on the next slide. So let's look at this flip chart. Okay, let's convert that binary bit I just had, 0, 1, 0, 0, 1, 0, 1, 0. So on the flip chart, we're going to flip up the ones onto the zeros so that our bit on the paper matches the one above. So if you look here on this paper, I have 0, 1, 0, 0, 1, 0, 1, 0. That matches what I have up here. Right? Now we're going to add the decimal values that are shown. So here I have 64 plus 8 plus 2. If I add all those up, I get 74. And so the number in decimal is 74. So if I say to you, convert this, you flip the tabs up, add them up. Oh, well, that's 74. Pretty simple. Now, when we go the other way, if we're going from decimal and we want to make it to binary, it's a little bit more tricky. Right? It's going to take just a little bit more thinking for us to do. We can't just look at the flip chart, flip a bunch of tabs, and say we're done. We've got to do a little bit more work than that. But we can still use that flip chart. So we're going to use the number 47 here, and we're going to convert that over to binary. So to start, we're going to flip up the number that's closest to 47, in this case 32. Now you can't flip up 64 because that's larger than that. And that's not going to work. You have to flip the closest number that's smaller than that. So I'm going to start up by flipping 32. Now we are representing 32 but need 47. So we're going to do 47 minus 32 to find out how much is still left. The answer, of course, is 15. So now we're going to flip up the next biggest number closest to 15. In this case, 8. Remember, you just can't go over because 16 is really close, but 16 is larger than 15, so you can't flip it. So now I have 32 plus 8, which of course is 40. So we're representing 40 now, but we want 47. So we do 47 minus 40, find how much left. We have 7. So now we flip to the next biggest number, which is 4. And you can see how this pattern is evolving. So we're going to go ahead and flip the remaining tabs. So 4, 2, and 1 in order to add up to 7. And that should give us our binary answer, 0, 0, 1, 0, 1, 1, 1, 1. And that's really all that's to it. Congratulations, you now know how to convert from decimal to binary and from binary to decimal. You know how to do both of them now. And that is all that there is for this lesson today, folks. Until next time.